Hi everyone, my name is Irene. I'm a student at Williams College, and then so for my project, I modeled the dynamics of bio-inspired inline swimming. What does that mean? Well, here's a little video. These are two fish from my lab, and we can see there's a fish in the front who's flopping at a constant velocity, and we see there's a fish in the back downstream somewhere who is flopping and stopping, flopping and stopping. As it flaps, it gets closer to the leader, and then as it stops, it drifts back a little bit. So this process is called intermittent swimming, and it consists of two phases. We have the burst phase and the coast phase, in which you just observed in the burst phase, the downstream swimmer generates thrust and moves forward, closing the separation distance. And then in the coast phase, the downstream swimmer stops, usually for sensing purposes, and then the separation distance increases. So my goal this summer was to model the dynamics of this inline swimming distance. And by doing, in order to do that, I used a mathematical model to represent the system and the dynamics, how it's changing. And I did this with two models, first being the constant thrust model, and then my second one was the sinusoidal thrust model. And essentially the process for each one was that I set up equations of motion and then analyzed them to understand exactly the dynamics. So the first thing I did was I assumed in the constant thrust model that the thrust generated by the downstream swimmer was just a constant. So just imagine it just goes forward and then stops, goes forward, stops. So here's a free body diagram of the downstream swimmer. And then using Newton's second law, I have these equations of motion for the burst and coast phase. And then in order to model the relative separation distance, I then incorporated the upstream swimmer, the little leader fish, who is moving at a constant velocity u, and then thus derived those equations. And then I analyzed those differential equations to obtain these analytical solutions to the differential equations. You don't need to worry about the details of this, but I use these in order to produce what's called a discrete time map. And the discrete time map's purpose is to be able to assess the state between each cycle, one cycle consisting of one burst phase and one coast phase. So this tells us the position at the beginning and end of every single cycle. Now with discrete time maps, I wanted to solve for the fixed points and understand the eigenvalues. And discrete time maps are a little different from like continuous flows as we are usually accustomed with. Discrete time maps, in order to solve for velocity, or to solve for fixed points, we set the position and velocity at the beginning of one cycle to be the same as the position and velocity at the end of the same cycle. And then I obtain fixed points for position, velocity, x star, and v star. And then in order to analyze the eigenvalues, I simplified my map down to a discrete time map of variations. So because I have now the fixed points, I can analyze the deviation from the fixed points. So greatly simplifying the previous discrete time map you saw there into this nice two-state linear system. And then I got these eigenvalues here. So lambda 1 and lambda 2, we have 1, and then this is a positive real number that's less than 1 due to the parameters. And then with discrete time maps, the conditions for stability are that if the eigenvalues are, if all the eigenvalues are less than 1, absolute value are less than 1, then the solutions associated with it are stable. And then if the eigenvalue, if there's an eigenvalue that's equal to 1, then the solution is marginally stable. So lambda 2 is associated with v star, which is some number that we can calculate using those parameters. And then what this tells us is that the velocity is stable, and eventually, no matter the initial velocity, it will converge to some certain, whatever v star is. And then the actual differential equations dynamics do not depend on initial separation distance, hence the lambda 1 being 1 and is associated with x star. So no matter the initial separation distance, the distance will eventually converge to some constant value. Here are the plots for my constant thrust model. You can see there's distance up there. Red represents the burst phase, blue is the coast phase. The distance kind of cycles in and out. The dots represent the discrete time map. And the same for velocity, we can see it converges to my fixed point, the dotted horizontal line, and stays there. This is a phase portrait plotting distance and velocity. And then so here, this are the initial conditions. You can see it has spirals into this little stable loop, showing that this system is stable. Now, moving on, we slightly reevaluate our assumptions. We assume now thrust to be a sinusoidal function that is dependent on the separation distance. This is due to previous studies that have found that the upstream swimmer produces a wave that generates our sinusoidal thrust term, slightly altering our equations. Now they are nonlinear, so we can linearize the system with a Taylor approximation for sin x, and then this makes it easier to find the analytical solutions. And I plotted the linear approximation with the actual numerical solution, and we can see it's pretty accurate on the left. And then even in extreme situations, the solutions converge. Now, here are the analytical solutions for the burst and coast phase, and I generated a discrete time map. So ideally next I'd solve for fixed points, but sometimes just due to certain parameters, you can't really find the fixed points as easily. And then so I used MATLAB's function called Pareto search to numerically find the fixed points. I also plotted the distance and velocity plots. I messed around with them a little bit to find where the distance and velocities converge to. So based on these numerically determined fixed points, you can see again, the distance converges to some certain value. And then also, so does the velocity, it converges to a fixed point. And this is again, similar to the constant thrust model. Our initial conditions spiral in to this stable loop that then we're permeates. So here is a little animation with the sinusoidal thrust model. So the sinusoidal thrust model gives us a model of synchronous flapping between the two fish. And then you can see in the red, against the burst phase, blue is the coast phase, and then they're moving to the left. And yeah. So my future work, I'd be interested in analytically solving for fixed points and eigenvalues in the sinusoidal thrust model. I'd also be interested in constructing a bifurcation plot to see how the solutions change as T0 varies. And then lastly, because I looked at synchronous flapping in my sinusoidal thrust model, I'd be interested in looking at asynchronous flapping, in which we include terms such as the phase offset. And also I'd be interested in a nonlinear drag term, as well as looking at flapping amplitude variation as we see here. And then I'd like to thank my advisors, Derek Haley and Rose Gebhardt, and then thank you to the Trend program, Daniel Serrano, and thank you.